I mentioned division of power series here, but so far we have only seen multiplication. So now let us go ahead and deliver the promise of this title and see what division of power series would look like. So to make an illustration of the division of power series, let us answer the same question. Find the first 3 non-zero terms for another very familiar and useful function, tangent x. So doing this using the definition would be okay. Tangent doesn't have very complicated derivative, but for high order derivatives it wouldn't be particularly pleasant either. So what we're going to do is we'll think of tangent x as the ratio of sine over cosine, and use the fact that we have Maclaurin series for both sine and cosine. I should probably be more precise here and say the first 3 non-zero terms of Maclaurin series for tangent x. Alright, so what are the Maclaurin series representations for sine and cosine? That is something you should know by heart at this point. And here they are. So we have sine x, which starts with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then the next term comes with a minus. Cosine x starts off like so, as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then the next term comes with a minus again. So what we will do next is pretty unexpected. We will perform basically long division as if these infinite power series were polynomials. How would that work? Well, we just put the ellipses after the terms in our series and pretend they are not there. Right? So all the subsequent terms are not important. We only care about the first 3 terms of this ratio, so we are taking only first 3 terms in the numerator, first 3 terms in the denominator, and then dividing them using long division, pretending they were polynomials. So that means we have to divide, let's see, x minus x cubed over 6 plus x to the 5th over 120. So these are the x cubed over 3 factorial and x to the 5th over 5 factorial. So this has to be divided by, well, maybe I have to make this a little smaller. This has to be divided by the expansion of cosine, which starts off with 1 minus x squared over 2 plus x to the 4th over 24. So that is x squared over 2 factorial and x to the 4th over 4 factorial. All right. So, and everything else, all the subsequent terms are, we pretend, not there. So the result of dividing x by 1 gives us x, and then we subtract x times 1 minus x squared plus x minus x squared over 2 plus x to the 4th over 24. The product of this x with this expression. We're subtracting x minus x cubed over 2 plus x to the 5th over 24. All right, so this cancels the x's as expected. So that's precisely what should happen when you perform long division. So the highest order term cancels. Here we have minus x cubed over 2. So that means we have x cubed multiplied by 1/2 with a plus, minus 1/6 with a minus. So the plus 1/2 comes from minus times minus over here. And so that is again 1/2 minus 1/6, giving us 1/3. Right, let's see what's going on over here. So we have 1 over 20 minus 1 over 120 minus 1 over 24. So that would be 1 over 120 minus, let's see, 1 over 24. That is 5 over 120. So I have as a result minus 4 over 120. So that would be minus 1 over 30 x to the 5th. Okay, now this remainder must be divided by the divisor here. So I have to divide 1/3 x cubed by 1. That gives me plus 1/3 x cubed. And then I'm subtracting 1/3 x cubed times the divisor. So let's see. What I'm subtracting is 1/3 x cubed minus 1/6 x to the 5th. X to the 5th. And then I have plus 1 over 72 x to the 7th. Great. So this reveals the final remainder. So since in principle we have lower order terms here after x to the 5th, it's just we are not writing them, we can forget about this x to the 7th, it's a higher order term, and perform the subtraction remainder minus this expression here, like so. So the leading order term again cancels. By subtracting these two, I will have 1 over 30 minus 1 over 6 x to the 5th. So I have 1/6 minus 1 over 30. This minus and this minus giving me a plus next to 1/6. And then I'm subtracting, this is 5 over 30 minus 1 over 30. The difference gives me 4 over 30. Or 2 over 15 if you like. And so you have 2 over 15 x to the 5th plus whatever the remainder is there. And then we see that the next term of the quotient will be obtained by dividing 2x to the 5th over 15 by 1, right? So here we have plus 2 over 15 x to the 5th. Great. So this gives us the 3 lowest order terms in the ratio, in the tangent x, which is precisely what we were looking for in this example. Okay, so the answer then is this expression over here. These are the 3 lowest order terms in tangent. So let us write the answer down. We have that tangent x is equal to x plus x cubed over 3 plus 2 15th x to the 5th plus some other terms. And so here it is. This is the beginning of the Maclaurin expansion of tangent x, and this is something you can use to compute limits. So even this short piece of the Maclaurin expansion gives you the ability to compute, say, limits that involve tangent. This can be used already to compute limits with tangent x. And we saw how to do that right here when we evaluated this particular limit. So in precisely the same way, you can replace tangent x with this expansion when x goes to 0, and that will be a viable way to compute limits. Now, how does this method compare to just using the definition? Well, for tangent x, I would say it's about on the same level of difficulty as using the definition, but for even less pleasant combinations of sine and cosine, so for instance, something like 1 over the product sine times cosine would be much easier to compute Maclaurin expansion for using the Taylor expansion for using the Taylor expansion for individual factors. So in many cases, this method will be competitive to just use the definition, especially if you only need the initial terms, right? This was the case here. We only wanted the first 3 non-zero terms of this function. And this also gives you another way of illustrating in what sense power series are very much like infinite polynomials.